Let's start the recording, and I'm going to share you my blank screen first. Okay, now in blood typing, typically, of course, if a blood type has an A antigen on its surface, we would say, what kind of blood type is this? If it has an A antigen on its surface, the blood type would be type A, good. Now, if it has a D antigen on its surface, what would this blood type be? A positive, very nice, good. Now, interestingly, the A antigen is sugar, okay? Is glucose or mannose, that kind of thing. It has a sugar moiety. Okay, we call that sugar, and different kinds of sugar that makes it the different A. Okay, so we call this as A antigen, right? In the future, when we talk about the immune system, an antigen. Let me write this down. An antigen is anything that can elicit an immune response. Okay? So what that means is that when you have a protein or sometimes lipid and it stimulates it so that now the B cells and T cells proliferate, we call that an immune response. Okay? And a lot of antigens are foreign, right? But some antigen can be on the surface of your own antigen, so we call that self-antigen. An antibody that binds to self-antigen oftentimes will lead to autoimmune disease. And we saw that in myasthenia gravis, for example, how the antibody is binding to the acetylcholine receptor. It turns out that we have preformed, okay, AB is antibody, okay, AB is antibody. Antibody against, so we're just going to write this mean against ABO antigen. The question is why? Why do we have these preformed antibodies? And on the other hand, we don't have preformed antibody against the D antigen. This is normal. This is normal. Typically, you don't have the antibody unless your body is exposed to something. Okay. Now, the first question is this: why do we have preformed antibody to ABO antigen? Does anybody know? Does anybody know? Okay. Now, it turns out that people believe that you as a kid, take milk from the mother, and the milk has bacteria. This is just normal bacteria. It doesn't hurt you at all. Okay, so we call this bacteria or normal flora. And then and then you're going to produce antibody against bacteria. Against the bacteria. But then those antibody then are specific or very similar to ABO antigen. So that's why you have it. But here's a very interesting phenomenon that we see in when we're talking about immunity, and that is B cells or T cells. So the cell that produces the antibody are B cells, okay, B lymphocyte. Now, if they are exposed to your own self antigen very early, then you don't react to it. So any B cells that reacted to self antigen is clonal deleted. Okay, clonal means that clone is removed from your body. Clonal deletion. Clonal deletion. So let's say, for example, in this guy, right? Initially, this guy here, initially he might produces the anti-A antibody, right? Antibody or anti-B antibody from drinking milk from his mother, okay? But the B cell that produces anti-A antibody, this antibody can react to its own self-antigen, so it's clonal deleted. So that's why it's removed, right? And so the A person, blood type A, have anti-B antibody, right? So you can say, okay, suppose that this person is AB, right? And it's a B antigen on the surface. Normally he would have anti-A and anti-B antibody, but it's clonal deleted, so then he doesn't have that anymore. So the AB in the body do not have any antibody. Now suppose that this blood type is O, let's say here is O, so drinking mother milk will lead to anti-A and anti-B antibody. And because it does not see self-antigen, it remains. You see that? So that's why you have that preformed antibody. The interesting thing is this, right? So let's say this guy now blood type is A negative, right? A negative. That means he never see the D antigen. Never see the D antigen, which is a problem, because had he been, let's say, A positive, right? Let's say this is the D antigen, and this is the A antigen. So any B cell that produces anti-D antibody, the B cells that produces anti-D antibody potentially can react it to its own self-antigen, so it's clonal deleted. It's clonal deleted. So if if guys, we don't care about you, right? It's only the female, right? Female. So how many of you here know that you are Rh negative? Female. Female Rh negative. How many of you? We have one person, Tina. Johanna, you have a question? Or you are Rh negative? Now, female who is Rh negative has to be careful. Okay. Now, if you're Rh positive, either male or female, you don't have to worry. Okay, because you're not going to have any D antibody, anti-D antibody. Male Rh negative, that's fine. Okay, but make sure that when you get blood, you get Rh negative. The problem with the female is that, yeah, if you're female Rh negative, here's the problem. Let's say that in pregnancy, during pregnancy, you have an Rh positive child or fetus, Rh positive fetus, right? Typically, the first pregnancy, no problem. Second pregnancy, when we say first pregnancy, no problem. Second pregnancy. The second pregnancy might be a problem is because during birth, right, after the first pregnancy here, she gives birth, and the fetal blood mixed with the maternal blood. And that's when she sees the Rh positive, right? Not utero, but at the delivery. So at this time, we call it sensitized. So her body exposes to the Rh factor for the first time. It's going to produce this now anti D antibody. So if her second pregnancy, her child or the fetus, right, the newborn is also Rh positive, the antibody that she's produced in the first pregnancy then can cross the placenta and destroy the fetus. Okay, that condition is known erythroblastosis fetalis. Blastosis fetalis. Okay. So erythroblastosis fetalis is also another name for his hemolytic disease. Hemolytic disease of the newborn. So the child also might born, and then because the child's get his blood from the mother, next time we're talking about, there are 5 classes of antibodies or immunoglobulin, but the only one that can cross the placenta is IgG. So that IgG class of antibody that the mother produced can cross the placenta and destroy the fetal blood. Okay, and then the child could be die of lack of blood. Someone have a question statement? That is why it's given RhoGAM shot. Yeah. It's fairly common. I don't know the statistic, but I would say roughly about 1,000 births or so. There's a female that carry an Rh positive child. She's Rh negative. And you're right. So what happened is that after the first pregnancy, who says this? Yeah, Tina. So there's an antibody called RhoGAM. Okay, GAM stands for the IgG immunoglobulin. Okay, GAM. That's what immunoglobulin is. Binds to the Rh factor. So right after the pregnancy, you see the fetal blood here. If you give the antibody to it, so the antibody in essence remove the fetal blood so that the mother never really sees it, right? If she doesn't see the Rh factor, she won't produce any antibody. So then it's fine. Okay, so after the second pregnancy, you give the antibody, and later on we will see is that there is kind of immunity. When we say active immunity, that's when your body makes the antibody. But when you receive the antibody, in this case, is called passive immunity, right? Because she's not making the antibody, she's receiving the antibody through this right here, ROGAM. Okay, so, if you are Rh negative, you kind of have to be worried. But I have some suggestions for you. One, what you should do is you should screen your husband or potential father, right? Say, are you Rh positive or Rh negative? If he's Rh positive, forget it. I'm not marrying you because I can have this problem, right? You can risk it, or you can say, okay, I'll just marry an Rh negative guy, and so that the fetus will never be Rh positive because you're negative and he's negative. Now, guy, on the other hand, right? If you are Rh negative and she say that, and she carry an Rh positive child, where does Rh positive come from? From the father, right? And she's telling you that, hey, this is your child. He's like, no, the child is Rh positive. I'm Rh negative, right? So he's not my child. So she's just a gold digger, right? So that's hemolytic disease of the newborn. So be careful. All right. Okay. Let's go on with the next discussion. So today we're going to talk about the heart. Okay. I think some of you are in my lab, not all of them, but if you are in my lab, please remember to submit the frog electrophysiology worksheet. I don't know how are the other instructor in your lab is asking you to do that. Okay, so today's lecture is focused on the heart, but the heart is part of the cardiovascular system. Cardio's heart vascular system is this network of blood vessels. Sometimes what you see is like the cardiovascular system will include the specialized connective tissue travels in it, which is also the blood. Okay. The heart, the major functions of the heart, of course, is to pump blood, but it doesn't have. It is in fact it has two pumps, right? One pump on the right hand side and one pump on the left hand side. Since the pump on the right hand side pumps the blood to the lung, right, and it comes back to the heart. This is known as the pulmonary circuit, okay, to the lung and come back to the heart. Okay. Now, blood on the left hand side pumps this blood throughout the body, right, and it comes back to the right atrium. You see, this is known as the systemic circuits. So there's two pumps. The right hand side pumps to the lungs, and the left hand side pumps to the general circulation. And since the lung is relatively short, I mean distant wide to the heart, very close to the heart, the right hand side of the heart does not need to generate a lot of force to cause the blood to flow. We call this hydrostatic pressure, right? On the left hand side, however, it has to have a greater force, and that force, I meant the hydrostatic pressure, which is systolically at 120 millimeters of mercury and diastolically at 80 millimeters of mercury. So if you look at the heart, right, the heart is divided into four chambers. This chamber up here is known as the right atrium. This one down here is known as the right ventricle. This one right here is the left atrium, and this one is the left ventricle. And you can see here is one key difference, that the left ventricle wall is thicker from the right ventricle wall. Okay. Now, here's the heart. And sometimes, if you turn this heart around, it's harder to tell, what is the right and what is the left. Okay? So one good way, what you could do is that you use your finger and you push it on it. The left ventricle will have thicker wall. It's going to be, more resistant than if it's soft, right? by the guys. If you guys are doing barbecue, I learned this trick where you do is, in barbecue and you meat, um, typically rare meat is very soft, but well done is very tough, right? And so you can push on your meat to test to see how tough it is, and or how soft it is. If it's soft, it's rare, but if it's tough, it's pretty well done. So one way you can do that is you take your thumb and your pinky, touch it like this, okay, and you push it on this muscle here. Um, right, you push on it, and you can see how hard that is. Okay, that is considered as well done. And you push the thumb and the pointed finger, push it. You can see how soft it is. So that's rare. So you got your rare meat here, and you got your well done here. So this same thing is say, okay, when I push on this is the right ventricle. Sorry, yeah, this is the right ventricle, and this is the left ventricle. Left ventricle is more muscle, it's more resistant, it's harder to push than on this side. Okay, this side it's going to be less muscle wall, so it's be softer than this side, will be thicker. Typically, when the heart it sits in the mediastinum behind the sternum, of course, and this part right here is called the base of the heart, and this is the apex of the heart. It sits in between second and fifth intercostal, which is very important, right? Actually, I have it here. So here's the base of the heart, and here's the apex of the heart, which kind of sit a little bit above the diaphragm. And you can say here's first intercostal, here's second intercostal, third, fourth, fifth intercostal. Fifth intercostal is the apex of the heart. Second intercostal is the base of the heart. Okay. It sits on the diaphragm. It has a serous membrane. Does anybody know the serous membrane that's surrounding the heart is called? The serous membrane that surrounds the heart. Pleura? Are you kidding me? Ask Andre. Pleura refers to lung. Okay, it actually is. Yeah, good. It's pericardium. Pericardium if it's a serous membrane, it has two layers, right? What are the two layers of the serous membrane? What are two layers of the serous membrane? You remember? All right. It's known as the visceral layer. Yes, and visceral and the parietal. Now, it turns out that if you take the heart, right, the heart actually has three layers, if you will. Okay. So the innermost layer here, that's easy to find. That's the endocardium. Endocardium. And you have the muscle layer. This is the myocardium. And then the outermost layer here, this is the epicardium. Now the heart, of course, is going to be surrounded by the serous membrane, and the serous membrane has this layer and this layer. Okay, this is the parietal layer. Parietal is outside. Parietal pericardium. And the visceral pericardium. Visceral pericardium. It turns out that the visceral pericardium, okay, oh, and by the way, there's fluid here, it's called serous fluid. So it allows the blood, it allows the heart to contract freely, reduces the friction within the pericardium. But it turns out that the epicardium and the visceral pericardium is so tight, it's the same thing. Okay, so that's one question already. The visceral layers of the pericardium is very similar to the epicardium. Right, so that's one question in the exam. And you can see this here. All right, now the layers that's going to surround the heart, you can see here, cover the visceral layers of the pericardium, which is the visceral layers here, and here's the parietal layer, a fibers, a layer of the parietal layers of the pericardium here. Okay, it's kind of hard to see, so what I'm going to do is I'm just going to blow it up, and you can see here. Okay, here's the endocardium, here's the myocardium, and here is the epicardium. All right, and the epicardium sort of like, you know, it's considered same as epicardium is the visceral layer. All right, so here's just the serous membrane. Right, you have your parietal layer out here, and it turns down to becomes the visceral layers of the pericardium. So the visceral layer is the same thing as the epicardium. Okay, now the heart has 4 chambers, of course. The 4 chambers are this one right here, right atrium, right ventricle, left atrium, and left ventricle. Okay, I know this is left ventricle because it's very thick wall. Okay, in you know, if we meet in person, we usually look at the sheep heart to dissect the sheep heart to see, you know, which one is the left ventricle and which one's the right ventricle. And oftentimes it's presented so that, you know, on your right hand side, the left ventricle. Well, I'm just going to show it the other way. I flipped it around. And so this side is the left ventricle. And the student, you have to pay attention to the thickness of the wall of the ventricle. Otherwise, you're going to get it wrong. And the heart has 4 chambers, but also 4 gates, if you will. What do you call these? The semi-lunar, so 4 valves. It has 4 valves. Okay. The valve that you see here. Okay. Now that valve is known as the right atrial ventricular valve. Okay. Right atrioventricular, right because it's on the right hand side. Atrial because it's between the atriums and the ventricle. On this side, right? Actually, more like here is your. Show you something. Yeah, so it's more, I'm just going to remove this. It's just this valve right here. This valve here. That runs between the left atrium and the left ventricle. We call that the left atrioventricular valve. I like to ask this question and make sure you do not forget this. The right atrioventricular valve has another name, which is, it has basically 3 cusps. It's known as the tricuspid valve. The left atrioventricular valve only has 2 cusps, so we call it the bicuspid valve. And because it looked like some, a hat that a religious symbol wear, that hat is known as the mitral valve. It's the same thing, mitral valve. Mitral, same thing. Now, easy way to remember is to write this two animal, rat and lamb. There's no reason why you should get this wrong. Rat stands for right atrioventricular tricuspid valve. The lamb is left atrioventricular mitral valve bicuspid valve. All right, so here's the walls of the heart. We are saying the epicardium is the same thing as the visceral layers of the pericardium. Myocardium is the thick muscular endocardium is the innermost. That has the layers of endothelial cell. Okay, epithelium, but it's the endothelial cells. Okay, now the myocardium is interesting. This myocardium get its energy or ATP for contraction mainly by cellular respiration. It does not involve get its ATP from glycolysis, because if it does, there's a tendency that you can make lactic acid and then you can go into fatigue. And you don't want your cardiac myocyte to go into fatigue, right? So this myocardium, or in fact the whole heart, rely ATP from cellular respiration. That means that it's very critical that the heart has constant supplies of oxygen, right? Without oxygen, right? Let's say we will see that the coronary circulation is a network of blood vessel that supplies the oxygens and nutrients to the heart. If one of those coronary artery is blocked, then that means that it won't get distant from that blocked site. The muscle won't get its oxygen, and then it's going to die, right? So under hypoxia condition or anoxia, you can get the cells can go into what we consider as myocardial infarct. Okay, myocardial infarct, like a heart attack, myocardial infarct. And then if it's died, it won't contract well anymore, and then your blood won't flow, and then you will die. All right, so here's to show you the walls of the heart. The endocardium, which is this right here. The endocardium have a layers called endothelial. Endothelial cell. Now this is very interesting. Give me a second. The innermost lining of the heart, the endothelial cells of the endocardium, is continuous. So the blood leaves the heart through this right here, called the aorta. The aorta is like any blood vessel will have three layers, right? We're going to see later on. The outer layer or outer coat is called tunica externa. The middle layer is known as tunica media. And then the third layer is called tunica intima. Intima or interna, that's fine. So you say cross section of the heart, you have this layer right here is the tunica intima. This right here is tunica media, and then you have your tunica externa out here. Okay. But the point I want to make is this right here, the tunica intima would also have endothelial cells. And this lining of endothelial cells is continuous from inside the heart to the artery, and the artery gets smaller into the arterial gets smaller into capillary. Now venous return is venual is back into the vein, back into the heart. That inner layer that has endothelial is continuous from artery, arterial, capillary, venual, veins, and back to the heart. All right. That and it is very smooth, and it's smooth. It allows us the blood to course through this very fast, at 5 liters per minute, for example. That's how fast the blood is flowed. That's a cardiac output equal to the amount of blood that you have per minute. That's how much heart efficiency usually pump is about 5 liters per minute. We can talk about that a little bit later. Let's look at the anatomy of the heart. As you can see here is again the parietal layers of the pericardium, right? And here is the visceral layers of the pericardium. How the visceral layer is actually cover the coronary artery here, coronary artery and coronary circulation. So typically, if it's low hypoxia, right, and the way that the oxygen will get these cells will get its oxygen if it's diffused from this blood vessel. It's diffused, right? And the question is, let's say here's zone 1, here's zone 2, and here's zone 3. So if there is hypoxia, okay, that means low oxygen. Hypoxia. Which zone? Is it 1, 2, or 3 that you will probably see the damage first? You want to do a poll? All right, let's see what the people say. All right, I'm going to run a poll here. So let's say if there is hypoxia due to a blockage of coronary artery, which area would most likely affect first? So 1, 2, oh, sorry, or 3. All right, let's start this poll. Let's see, how many of you think is 1? How many of you think is 3? Because one person says 3, and then everyone follow along. And all 13 of you will be wrong. I don't know if you guys see the result. Okay. Here's the result. Right. Oh, now you changed your mind. Good. Oh, good. Yeah. Okay. All right. Stop. I'm going to stop this poll. Yeah. Actually, come on. It's number 1. Okay, because oxygen has to diffuse down to this. That's a further diffusion. If you have a little bit of oxygen, these cells can survive because it's near it. Oxygen has to travel all the way down to here. So number 1 will be affected first, right? So clinicians will often refer to as endocardial myocardial infarct. So subming is underneath of that. Okay. Okay. Good learning lesson. I don't know if I throw that clinical question in, but alrighty. Let's move on. All right, here's other chamber. The right atrium receives the blood from three sources: inferior vena cava, superior vena cava, and coronary sinus. Now, coronary sinus take drainage from the coronary circulation. Okay, take drainage from the blood vessel that is surrounding the heart. That's what coronary means surround the heart. Blood from the right atrium goes into the right ventricle through the tricuspid valve or atrioventricular valve, right atrioventricular valve. And blood actually leaves the ventricle, goes into the lung, but it goes into the pulmonary semilunar valve. So the pulmonary, this is known as half moon, semilunar valve. This is the valve between the right ventricle and the lung, the pulmonary trunk, if you will, and then to the lung. Blood coming back from the lungs to the pulmonary veins and into the left atrium. Blood from the left atrium goes into the left ventricle via the left atrioventricular mitral valve or bicuspid valve, and blood in the left ventricle goes out into the aorta, and there's a fourth valve that you see, okay, right here, and that valve is known as the aortic semilunar valve, aortic semilunar valve. Okay, so there's a four valve, right? The right atrioventricular valves from the right atrium and right ventricle. The left atrioventricular valve is between the left atrium and left ventricle. The pulmonary semilunar valve is from the left, so the right ventricle and pulmonary trunk. That should be here is pulmonary trunk, which goes into the lung, and then blood from the left atrium goes to the left ventricle via the left atrioventricular valve, and blood from the left ventricle out into the aorta goes through the aortic semilunar valve. Okay. And here, as you can see, tricuspid valve. This is the right atrioventricular valve. And a lot of these valves one-way valve. In other words, blood from the right atrium goes in the right ventricle. It doesn't go backward. Okay? Blood in the right ventricle do not go back into the right atrium unless there is a defective valve. But typically, it won't go back. There's no regurgitation. Okay? In a case we call it valvular insufficiency, then the valve is damaged. The blood can gush back from the ventricle into the atrium. Typically very common in the left ventricle. Blood in the left ventricle can go into the left atrium. Pulmonary valve, pulmonary semilunar valve, you can see here, is between the right ventricle into the pulmonary trunk. Pulmonary trunk branch into the pulmonary artery, and so forth. Mitral valve is between the left atrium and left ventricle, and blood leave the left ventricle through the aortic semilunar valve. Okay. And you can see here. Interestingly, here's an interesting thing you guys need to know. Okay. Oftentimes, when we talk about artery, okay, so pretty much all arteries carry blood away from the heart. Away from the heart. And all veins, pretty much all veins, carry blood toward the heart. Okay. Now, because artery generally is called, we call this the arterial system. Okay. Arterial system. Artery. Now, vein, on the other hand, is the venule system, right? Now, the arterial system, particularly the heart pumping blood out, that blood is oftentimes carry oxygenated blood. So oxygenated blood. And in the case of oxygenated blood, oftentimes people would draw the blood vessel as red, okay, the red. Okay, this picture. Now, venule system tend to carry deoxygenated blood. And deoxygenated blood tend to be, blue, so the blood vessel is blue, right? So you can see here, up here, you can see how these are deoxygenated blood. Superior vena cava, deoxygenated, inferior vena cava goes into the right atrium, right? And the right atrium goes into the right ventricle. Okay, this is your tricuspid valve, and from the right ventricle into the pulmonary trunk through the this is the pulmonary seminal valve, right? And then blood goes to the lung, it comes back, right, to the pulmonary veins into the left atrium, blood from the left atrium into the left ventricle, through the mitral valve, and blood from the left ventricle out into the aortic center valve. The way that if you want to see the aortic center valve, you have to cut deeper, like this way. So here's your aortic center valve. Okay. Now, there are some exceptions in arteries and veins, right? So not all artery carry oxygenated blood. Is that clear? All artery do carry blood away from the heart, but not all of them carry oxygenated. There are some exceptions. Okay. Let me write this down. So, not all arteries carry oxygenated blood. There are exceptions. Right? What are those exceptions? And then you can say, not all veins carry deoxygenated. There are exceptions. Right? Okay. Now, one of the exceptions that you see here already. Okay. This is known as the pulmonary trunk that becomes pulmonary arteries. This one on the right. Sorry, this is on the left. This one's on the left, and this one on the right. See, you can see how pulmonary artery, in this case, is an artery. It does carry blood away from the heart, but it's blue. It's carried deoxygenated blood, so that the deoxygenated blood can goes to the lungs, where it's get oxygenated. It comes back to the heart through this pulmonary veins, and pulmonary veins will carry oxygenated blood, right? So you can say here is that one of the exceptions is that pulmonary vein pulmonary vein carry oxygenated blood, and up here, pulmonary artery carry deoxygenated blood. Okay? All right, so there are other exceptions in fetal circulation, but I'll tell you later. All right, so one of the exceptions is here, pulmonary artery carry deoxygenated blood, and there's two pulmonary arteries, one on the right hand side, one on the left hand side, but there are four pulmonary veins, two on the left and two on the right. Heart valve, right? If you do so. If you cut the slice of the section you see here, you can actually see the, this is the valve right here, okay? This is the right atrium up here, and the valve here has cusps. This right here is one cusp, two cusps, and three cusps, for example. The cup is hold on to the heart string. The heart string here is known as 289ae, which is held in place by the papillary muscle. Okay, that's the papillary muscle here. And you see these valves right here. This is pretty much connective tissue. Okay, it's not muscle. In fact, here is also connective tissue. Here's connective tissue. Here's connective tissue. Here's connective tissue. Right. And this is a real heart superior view, so that if you look at, this is the anterior and this is the posterior. Right. On this side, you can see here's one cusp, here's two cusps, here's three cusps. So this is your right atrioventricular valve. Over here, you see only this one and this one. That's a bicuspid valve or mitral valve. This one up here is the pulmonary trunk, and this is the aortic seminal valve. You can see here. It's semicircle, but it looks like half circle. This little dot in the middle, this opening right here, is actually a lumen. So if the blood is inferior, right, come back out, this thing will collapse like this. So all of this will collapse. So you get this gigantic lumen. Okay. So it's just going to push against the wall, just like if I have a pocket, right? If blood is coming back, blood is from the below that goes up, it's just going to cause this push against the wall. Now, blood is trying to come back to the heart, for example. If you come back to the heart, this thing will be filled with blood, and this will be filled with blood, and this will be filled with blood, and so the lumen is closed up at the three areas meet. So that's why the blood cannot. So let's say for this one, in this case, as you can see here, it's kind of collapsed, right? There's nothing there. There's no opening there. So if this is filled with blood cannot go back into the heart because the opening is here is closed. This is just like a pocket. This is like a pocket. This is like a pocket. Now, if blood, on the other hand, below that comes out, this, this septum, this little part, it's going to push against the wall. It's going to collapse. Okay. Then you get this gigantic lumen. All right. Now, because of these connective tissue, all of this form what we consider the fibrous skeletons of the heart. Here's where you might see the fibrous skeletons of the heart. See all this? All of that forms just the fibrous ring to which the heart valves are attached. All of this is fibrous skeleton of the heart. Now, this is critical is because cardiac myocyte, you guys learned a little bit about cardiac myocyte, that it works together as one unit we call syncytium. Okay. And syncytium is because they have gap junction and gap junction is finds an intercalating disc, right? And so that it turns out that when the heart contracts, the two atria contract at the same time. And that is when one particular part of the heart depolarize, this wave of depolarize that has been shared through the gap junction. But that depolarization does not travel down to the ventricle because the fibrous skeleton prevent that signal from that occurring in the atria doesn't go down to the ventricle. Now that's a great purpose, and you will see why. Because if the heart functions to pump blood, it has to rest, right? Sufficiently, right? Rest meaning relaxation. It has to relax with sufficient time so it can be filled with blood, and so when it contracts, it eject that blood, right? If its relaxation is too short, right? So typical heart rate should be like loved up, loved up, loved up, like that, right? But if it doesn't relax, it's sufficient time, say really fast, like that, then that meaning that there isn't have time for the heart to fill with blood. Like that's a problem with tachycardia. In fact, when someone is going to fibrillation, is that the heart is flutters like this. I mean, it doesn't have enough time to fill with blood, and so it seems like it contracts a lot, but it doesn't do anything. It doesn't pump blood. Okay, so we will see that the atria contract so that it can push, any blood in the atria down. It's kind of like squeeze it so it goes down the ventricle, and then the ventricle contract is eject that blood out. Okay. All right, so I'm going to stop here, and you guys take a 5-minute break.